Yes,
It's
sir.
only for steadiness. Steadiness only we are used. So irrotational thing also. So only for irrotational steady flow. So in that case, this is constant we wrote. Okay, so now we actually started with this incompressibility. See, that is different. See, actually, this that's what I want to tell in this class. See, it looks like we are doing something which is irrelevant. So this at this juncture, so this we are at the some juncture where you have to see like out of the box. You just check kind of global view or eagle view. So you see where we are, where you are standing. Now you have to understand first. So we have derived those equations. Okay. So in the case of incompressible fluid, you have 5 equations, 5 unknowns. So as such, you have a fluid domain you have. So whatever fluid domain you have, you have PDs, you have 5 PDs, you have 5 unknowns. So in principle, you can solve it. That's what you have to. So the why we have taken one of the equation in the fluid. That is what is the equation of momentum, and we're trying to we're trying to resolve that one first. Right? We are integrating that one under certain conditions. What are the conditions that you have done? What are the conditions you have derived this one? For example, what exactly you have done to derive this Bernoulli equation? Yes.
Sir, for Bernoulli equation, sir, we take the momentum of barotropic fluid, sir.
No, I think what we have done is basically um, you have taken the momentum equation you have taken. So and you have written. Did we use anywhere del dot u equal to 0? We have not used, right? So
Yes,
basically, we have not done anything except we just rewrote, and now we put the condition that irrotationality will remove the term. Okay, irrotationality, if you use del cross u equal to 0, so that will give you nicely, you will get your Bernoulli equation. That is a constant. That is entire fluid. It is true. So it can be compressible fluid also. Compressible irrotational motion also it is true. Bernoulli equation. Where irrotational means you have a u equal to grad phi. So for scalar function, that's called velocity potential. Okay. So that velocity potential that we have seen, now what we consider is we don't remove the del cross u equal to 0, but we remove the dou u by dou t term. So that is why steady rotational motion we consider, and that gives you that along certain curves we will have some constant. That constant may be different at every time. Okay, that's what you have seen in last class. That is u square by 2 p by rho. The integral dp by rho. Now we see that is actually generally your rating. Don't feel that it is some kind of vague thing. Only if rho is a function of p. If it is given, you can calculate that integral dp by rho. That if you simplest terms, you consider that rho is constant. Okay, for any incompressible fluid or any fluid. Okay, so rho is constant. Then it is simply that integral dp will go this simply p by rho. Right? So rho is constant, comes out integral dp is nothing but simply p. So p by rho only you're going to replace. So this gz equal to constant. That is along the streamlines, you have a different constants. That term, that is the Bernoulli function. That's what you have seen in the last class. Okay. Irrotationality, if you put it, so the earlier time-dependent Bernoulli equation becomes this one. So that is the constant that is everywhere you have seen. Okay. See what is happening. Why do we need this one? So this is different entirely. Up to this point, it is different concept. So yesterday, I suddenly started something. I should have told where we are. So we just started this del dot u incompressible fluid we considered. And because of the CC del cross u equal to 0 implies there exists a velocity potential scalar function, no, such that u is grad phi. So in the incompressible case, there is a vector potential, if you want to call. So that is v bar, such that curl of that vector field is actually given as your u. So in this case, in 3 dimensions, if you actually see, this v exists by the Helmholtz theorem. So some v exists. Okay. So how do we know that this exists? Helmholtz theorem tells you that this actually exists, no? So I can always decompose as a rotational part and irrotational part. That rotational part, if you take, you have such a V exists. Okay, that is what is that Helmholtz theorem. And also it is not unique, because if I whatever that rotational part V, if I add some scalar function as gradient, you put it there, so that becomes curl of that gradient, so that is always 0. Okay, so for that reason this is not unique. So if it is not unique, you have to impose conditions on the domain. So on the boundary, if you if you work with this V, this is a vector potential, this is called vector field V. That is also called basically scalar. What is that one? That is also called vector stream function. If you really want to say, you say stream function. That's it's difficult to get this. Okay, so we exactly, you don't know how to evaluate this one. So in 3 dimensions, the problem is you can't work with this. You can't make any progress. So we left it there. Okay, so it is unique, but though it exists and it is not unique. So that's why. But if you do in 2 dimensions, so 2 dimensions, what is why it is this V is perpendicular to you? 2 dimensions, what we wrote is V is perpendicular to the flow plane. That is basically XY UV. So why do you know the reason why V is perpendicular to? If suppose U is only in the XY plane. Okay, flow is only the XY plane, means you have only UV component, Z component is 0 here. Del cross V. So this V is perpendicular to U. Why? Can you tell?
Yes, sir, because cross product is there, sir. So that is perpendicular to gradient and wave both also, sir.
Where is the gradient? Come again. See, U equal to del cross V. Now U is in 2 dimensions, 2-dimensional flow. So del cross V bar. What is that V bar? That V bar. What is that V bar? That V bar in 2 dimensions, it is actually, it's unique, right? Is it unique? Can you say it is unique?
Yes, sir.
In 2 dimensions. Why? See, we are seeing, you see, 2 dimensions. Basically, you see, if I put it like a V equal to only along the Z direction, if you consider, then obviously you are seeing that U is actually a function of X. Only you see 2 terms here, right? But what you have seen earlier is when you are doing del U cross omega, okay, omega is what? Del cross U and U, right? So when you look at that one, there U and the omega, that is U or del cross U. If I take V as U, del cross U and U need not be perpendicular, right? In 3 dimensions. But in 2 dimensions, they are perpendicular. That's what you have seen. No? Physically, you can feel, because del cross U means it is a rotational component with its own axis of the particle. So that way, if you are moving along the U direction, but depending on the plane, if you are only in the 2 dimension, there is only one plane. So the perpendicular thing will be U is always perpendicular to the del cross U. So del cross U is basically perpendicular. So something like here, del cross V, similar way, in 2 dimensions, del cross V is perpendicular to U. Okay, isn't it? So that means del cross U itself is U. Uh, del cross U itself is U. V is that U is actually perpendicular to V. Okay, so can you see that one? So you may not see physically, right? The del cross V. V is basically some vector field. If you take that along the z-axis, okay. So del cross. So the best way to see is there is not physically, you don't see it. So if I choose this V as like this, okay. So only as a z component, as a function of xy, that you call it stream function, then you see that basically del cross V is nothing but only in 2-dimensional flow. Okay, dou psi by dou y. So that's what we are putting UV. Okay, this is the only way you understand. Don't like earlier, no, you did no in the derivation of steady flow, right? In the derivation of that momentum equation you modified, right, for barotropic fluids, where U and del cross U, there you have seen based on that omega. So del cross U means omega, no? Omega and U directions, based on that you have seen. So the only reason here is if you take V as in the direction of Z, then obviously this V is then U will be del cross, that Z direction will be, once you take the curl of the only Z vector field that is only in the Z direction, obviously this is if you actually directly if you calculate, that is going to be in the XY plane. So in the XY plane UV, so UV is anyway unique, no? So the flow is unique. So if you can find your psi, obviously psi, if you can find such a psi is unique up to a constant always, right? So if I can here also, if I can multiply some constant V, if I take it as constant, then obviously U is 0, right? So if you add psi to some constant, for example, so then obviously the fluid may be, the flow may be unique, right? So if U is unique, so in that sense psi is not unique up to a constant, right? Psi, if you add some constant, still it doesn't affect to your flow. So that's how psi, you say it is a stream function, which is some sense unique. Okay, you have to understand this fluid mechanics sense. Okay, any questions up to here? Hello?
No, sir.
Fine, right? So why we say that stream function? Because along the streamline, this is always constant. This function is always constant. That's what we have shown. Dou psi by dou s. S is the parameter along that streamline. Okay. If you take it, total derivative you consider and divide by along that curve s, that is nothing but dou psi by dou s is nothing but that is actually grad psi dot product with the tangent, right? The tangent is dx by ds, dy by ds is nothing but along that tangent, no? That is tangent to the streamline. So the in that direction, it is actually the way you have done it, that is construction, that is equal to 0. So that's why psi is constant. So that's how you define this stream function. Okay. So for 2-dimensional flows, you are able to get some stream function as a scalar function here. Okay. Otherwise, you don't know what to do. If it is a 3-dimension, you really don't know how to construct your V bar itself is. See, V bar itself is like acting like a potential, that is like where it involves only 0, 0, some scalar function. Only third component only you put it as that vector field. Okay, V bar. So if you consider a 3-dimension flow, you cannot choose this way. Okay, you cannot choose this way. It may have other components. Suppose U, V, W, if you have components in 3 dimensions, del cross V cannot be this way. So you cannot say one function. So you'll have V itself is called the stream vector potential. Okay, vector stream function, you may say. Okay. So stream function in that case it won't be single scalar function, it will be vectorial function. That V bar itself is stream function. But you don't know exactly, that is not unique by the way, and that you don't know exactly how to find in the 3 dimension. Those who were not able to make any progress, that is the reason we didn't do anything there. Okay, 3 dimensions. Though we started and we say that Helmholtz theorem guarantees that there is a velocity potential V bar, and it is not unique, obviously, not up to the constant, including some more functions. Gradient of some scalar function, if you add to that V, that itself is, you are adding something. It's not constant. You're adding some functions, right? So that way, that V bar is not unique in 3 dimensions, and it is not. You don't know how to go ahead with your stream function. If at all you want, it's not stream function, stream vector potential. Okay, stream. You say it's a vector stream function. You can say. Okay, so that we don't know how to do. So under certain conditions, you can do. That depending on, if you consider the problem and if you impose the boundary conditions, maybe you can guarantee the uniqueness of that such a V bar. Okay, so you need to extra conditions for each of the problems. So V is not unique. So rudimentally you have to see that V is not unique. Okay, but in 2 dimensions, V is unique up to a constant. Constant doesn't matter. Constant will not affect, no, because UV are nothing but those derivatives of psi. So psi, if you take as long as constant, doesn't matter for you. Flow is not changing. But if you take V in 3 dimensions, there it is not unique because you're adding any gradient of any function. Those are gradient of V means it's another vector, right? So that you are adding, so that need not be constant. Up to here, fine, right? So that's what then we have given certain boundary, certain simple flows. Some examples that we have given. So one is the source sink, other one is simply a vortex flow we have given. So that's what we have seen. Okay, so this if we consider, if in this case, last class, what we have considered is suddenly we have done this Bernoulli equation, and then we immediately jump to this part. That is where you try to, for incompressible fluid, you are trying to derive the stream function that is given as your flow. In terms of stream function, you want to give your flow. That is not possible in 3 dimensions, but 2 dimensions it is possible. Okay, so that's what you have seen with 2 examples. Even in 3 dimensions, if you want 3 dimensions without, 3 dimensions, for example, source, sink, 3-dimensional source, sink, you can think, but you cannot choose this incompressibility. Okay, though you can start with this incompressible thing, but you cannot use your stream function. Okay, through stream function you don't do because it is 3 dimensions. No, you don't know that we will do directly from the Euler equation. So we will see that one 3-dimensional flows we will see. Before that, let us go back to what we have here. So what is that we have done here before this one? This looks like entirely different concept, right? Different topic. So you have chosen some, what is that, momentum equation you have taken. Under certain conditions, you derived Bernoulli equation. And for steady flows, you have used without irrotationality, you derived this is a constant. This is also called Bernoulli function, right? So what it says is basically if you rho is a function of p, rho is function of p, then you can evaluate this one, integral dp by rho. So there is nothing vague here. Okay, so you always consider simplest cases where rho is constant, so that you have this second term will become p by rho. So half u square plus p by rho plus g zeta is constant. That is basically what you did is you integrated the whole momentum equation and you solved that one. Okay, now you're left with, actually if you see this one, if you want to keep this as though you solved this over the full fluid. Okay, so if you think that you already solved this equation, one of the PDEs you solved in the full fluid domain. Now you consider the other equations in the full domain, and then you solve for one less than. Okay, so if you obviously you remove basically your momentum equation because you already solved it, right? You integrate it, right? Solve means what? Basically integration. So one of the equation you already integrated. So you will have 4 equations only left, right? Yeah, momentum equation already you have 3, right? 3 is finished, right? 3 finished. So you'll have 2 more equations. From there, you can calculate your P and what else you need? Rho, right? P and rho. So those P and rho only you have to calculate. So once you get the P and rho, if you see as a fluid domain, once you get P and rho, so you from this you can get the flow U bar. Okay, U bar square, U dot U. But generally what we do is or del dot U. So maybe U if you calculate from the other equations, okay, del dot U equal to 0, dou rho by dou T, right? That is from there also you can get U. So U and rho you can calculate. So this may give you actually P in terms of U. Once you calculated U from those equations, del dot U equal to 0, equation of that incompressible fluids only I'm talking about. Okay, though this is the equation that is valid for compressible also. So once you get that one, once you know the flow of the problem, so you can actually get the P also directly from this. Okay, so this is useful actually if you consider irrotational flows where you are replacing with a grad phi. Okay, so you have this grad phi mod square plus this is P by rho plus Gg equal to constant. That's what you have to do, right? And of course, dou U by dou T, if you can also consider dou U by dou T, then it becomes dou T of U I can replace with grad phi. So that's what you have, right? that grad thing, if you take it out finally, you will see that that's what is the Bernoulli equation you have. Okay. So there also, if you calculate your P, and now you consider the irrotation, incompressible also, del dot U equal to 0. You already you have a grad phi. So del dot grad phi is nothing but it's your Laplace equation. So you have a Laplace equation throughout your fluid. You have a Laplace equation that is 1 PdA. And now, so it is like, incompressible fluid. Think of only waters. And what are the equations that you have? Del dot U you already used. That is exactly del dot U is giving you this one. So your momentum equation is basically you integrated out. That is your Bernoulli equation that you only use in your boundary condition. Because eta also another, because moving boundary, no? So the boundary is actually moving for the waves, water waves, right? For the ocean if you consider water. So in the surface, because of the gravity Gg, there are some disturbances. Okay. So these are gravity waves. That's why there is nothing like, there is no flow because of G only. If you remove the G, there is nothing. It's like free. Okay. So G, because of G, you have some disturbance. That's your gravity will create some disturbance. That will give you motion. Okay. That will give you some flow. All those velocities of particles will get. Okay. So you have a Laplace equation on the surface. One is your kinematic condition. That is we already derived. Okay. So as a surface you have derived now. So xi equal to or zeta of x y is t equal to 0. Right? The z minus eta of x y t equal to 0. So you derived some kinematic condition because there is another unknown is coming into the picture, right? So in the problem, so that is your eta, surface elevation. So that along with this one, whatever you integrated, no, so the momentum equation, that is considered as dynamic boundary condition. So kinematic condition and dynamic boundary condition coming from this integrated Bernoulli equation, that is involving phi. So that is how you solve the waterway problem. So let me write now whatever I'm talking about. So we are deviating here. Okay. So that you now we are at this juncture. We are trying to get the information. So I left some information about this Bernoulli equation. So why did we integrate this momentum equation and derive some Bernoulli equation for irrotation flow and steady flow? Some Bernoulli function we derived, and we say that this Bernoulli function is constant. What for this is useful? Okay. So we'll see this one. The Bernoulli theorem actually gives you, this is a Bernoulli theorem where B is constant. This has some applications in fluid dynamics, so that you can easily see. So we'll try to touch upon these things. Okay. So right now, what I'm trying to say is for irrotational flow, we will use the what exactly, how this integration of this momentum equation helps to solve the problem. Instead of looking at the full waterway full fluid problem where you have 4 PDs and 4 unknowns, or 5 PDs, 5 unknowns, instead of solving that general setup, so if you assume certain irrotationalities, then your equation becomes a linear equation. That is your Laplace equation. So Laplace equation is basically your linear equation. So we'll first show that equation, how the equation becomes your Laplace equation. Let me show you that one first. Okay. So let me write it so that you will understand better now. So as you see, so we are considering only, let us say, we will go back to irrotational flow. Okay. So you have a irrotational flow. Irrotational flow. That means del cross U equal to 0 implies U is grad phi for some P of x, y, z, comma t. This is called velocity potential. Because U you are representing, no? So U you are representing as grad phi. So for example, that external force by the gravitational force there, that is called external force. That force Green's function, force potential, that is. Okay. Whatever you are writing gradient of Gz, no, Gz. That is basically a potential you may call, that is external force potential. So this is your velocity potential because U is represented as grad some scalar function. Okay. So this is what you have. Now, what is that you have? So because now you consider incompressible, for incompressible fluid. If it is compressible fluid, we cannot work. Okay, compressible fluid, we don't do anything. So though you have this one, this is your Bernoulli equation, you already solved it. Okay, for compressible fluid, what you will do? Now you see, as I said, for compressible fluid, you already what you have is basically compressible fluid means dou u by dou t. Dou u by dou t will be there as it is, right? Dou u by dou t is there, but without, only for steady flows only you can do, right? If you include that dou u by dou t term as it is in your rotational thing that we have done now, that Bernoulli function we brought in, dB, right? Grad b and plus dou u by dou t. That momentum equation, if you consider, you can't do anything. So it is like same as the original momentum function and whatever the other main equations that you have. Okay, total number of equations, number of unknowns. That way only you can solve it throughout the fluid. So these are something which special cases where you can actually solve. You can actually integrate one of the variables and one of the equations and try to simplify the problem. Instead of solving 5 equations, 5 unknowns, we're trying to solve a little bit different. So if you consider steady flow, so what you are seeing is here is u square by 2 plus p by rho plus gz equal to constant. That's what you got now. That is your Bernoulli function. Last class you have seen that b equal to constant. Of course, each constant is different for different streamlines. So that you already integrated out. So remaining equation you solve and get your u, so that you have a pressure is given in terms of your velocity. That is the advantage of these Bernoulli functions. Of course, for steady flows only. Now you are looking at even further simpler one that we already derived as a Bernoulli equation. That is for irrotational flow. And of course, once you have irrotational flow, you have already irrotational flow. You already have this one, and your momentum equation. You already have that one. So let me write that one before I write this incompressibility. So that it is in order. So once you have the irrotational flow, you already have momentum equation. Momentum equation becomes, you integrate, becomes Bernoulli equation, right? Bernoulli equation. Bernoulli equation, which you already derived, that is your dou phi by dou t, because it's a function of t also, plus a grad phi whole square. Square means dot product. Okay, that's the meaning. Modulus square, because it's a vector. Half of that. Let us look at this p by rho. Okay, grad p by rho, right? So that we have already written as p by rho. So this is, in this case, did we use here? We are only using rho is a function of t. So rho is the only maximum. So when you derive the Bernoulli equation, you are assuming either rho is constant or rho is only function of t. So only in that case you have, this is simply p by rho. P is a function of x, y, t. Okay, p by rho equal to external force. That is your external force. You call it as gz, right? So this is equal to gz minus gz. Let me put this side itself. So that is actually equal to plus gg equal to constant. Constant everywhere in the fluid. So this is what you have, right? Irrotationality means you have this one, and that actually the momentum equation becomes this Bernoulli equation. Now I consider nothing. I don't gain anything with this. Okay. So only what is that I gain here? This will give me, if I know how to get my u from the other equations other than this momentum, u is given as grad phi. So once you know u, I know what is my phi. So once you come phi, if you can substitute here phi, and of course dou phi. If you know phi, of course if you know u, it's not easy to get your, no, that's you have to integrate grad phi. How do you find phi? You may not know. You may use directly grad phi in this case, okay, to get p. But who will give you dou phi by dou t unless you know phi? So that is why to get phi, we will impose not just for any general fluid. So we will use for incompressible fluid. Okay. So now I impose also incompressible fluid. For incompressible fluid, that means you can think of water. That is del dot u equal to 0. Implies, what is the meaning of this? Del dot u is grad phi a scalar function which is equal to 0. So this is nothing but del square phi equal to 0. This is your Laplace equation. See, so far you have all your equations may be nonlinear, right? Of course, your mass equation may be, equation of continuity may be del dot u equal to 0, no? So this itself is like dou u by dou, so that is maybe linear. But here, the equation becomes linear here. So throughout the fluid, this is true, right? Now we have a Laplace equation. Okay, so for incompressible, we think of water. Okay, so now what you have? So this is del square phi equal to 0 in fluid domain. Now, what are the boundary conditions that you give to solve this phi? Now, one is now imagine your water. Okay, so think of this way. This is like water, incompressible fluid, and you have, because of the gravity, you will have a disturbance. That is what you are calling eta. Okay, that's your surface elevation. So you have this boundary condition. One of the boundary condition you already see it as kinematic boundary condition. Kinematic boundary condition you already given, no? How do we get z equal to? So this is your z direction, negative z direction. Z is equal to minus infinity direction. This one, so that you have z minus eta of xyt equal to 0. This is exactly your zeta of xy zt. That is the interface between air and what, your fluid. Okay, that is actually constantly changing. You don't know how it is changing because of the gravity, because there is no other external force you are considering. Kinematic condition, we already have seen that. What is the kinematic condition that you derived? Can you recall and tell me? Dou eta by dou t. Yes, dou eta by dou t plus u. That is the velocity component in the x direction into dou. What is the next one? Eta x. Dou eta by dou x plus v into dou eta by dou y minus w into dou z by z. Dou z by dou z, that is anyway 1. So that is why you get here w equal to 0. Isn't it? This is what is your kinematic condition at the surface. So now I know what is my UVW. So that is basically what you are getting is dou eta by dou t plus dou phi by dou x. Okay, is simply del phi dot product with eta x, eta y, and minus 1 equal to 0. So this is what is your condition. So what is unknown here? Eta and phi are unknowns. Okay. So I have some other things. So once you have this fluid, once you have a free surface, and you basically have eta is the surface elevation. Unknown. Okay. So of course unknown. Here we don't know how it is moving with time x, y, z and t, right? X, y, t. We don't know how it's moving. So this is an unknown. And phi obviously is another unknown. Phi is potential function unknown. Anyway. This is anyway another unknown. So for the Laplace equation, this kinematic condition, and also you give your this is where we use. So once you, whatever you integrated your momentum equation, that momentum equation, whatever here, that you are going to put it, you're going to use it as a dynamic boundary condition. Okay, dynamic boundary condition is actually your Bernoulli equation. So that Bernoulli equation I'm writing directly. That is your dou phi by dou t plus grad phi square. Square means dot dot. Okay, so this is modulus square plus p by rho. Simplest case where p is rho is simply a constant or function of t. Bernoulli equation is rho is function of t only. Okay, rho is function of t plus, of course, you have, because of the gravitation, you have the flow. Otherwise there is no other external force. Okay, or there is no flow as such. UVW, u vector is actually 0 without g. That's how it is. Okay, so g z equal to constant. So of course this constant, what do you do with this constant? This constant you can always, so what is that constant? throughout the fluid you are saying, no? This constant I can always observe. I redefine my phi in such a way that phi minus constant is actually your phi. You redefine your phi, redefine phi of xyz t as that original old phi minus this constant, whatever constant you say throughout, no, which may be unknown for you, but still you call this one, you absorb it here. Then what happens? This dou phi by dou t is same as this, simply this old dou phi by dou t only, right? That's the only thing. Anyway, grad phi is same as grad new phi is same as this grad old phi. That constant anyway becomes zero. Both are same. So whatever you can put it here, I can put it. So this constant I can remove. Redefine your phi in such like that, so that your equation basically will become dou phi by dou t plus grad phi. This is your new phi divided by 2 plus p by rho, which is function of t maximum or constant, plus gz equal to that is 0 now, because I took it this side. I absorbed it into phi. That constant I absorbed into that phi. So let me write this as rho of t, or rho is a constant, or t rho of t. So this is your dynamic boundary condition. So how many equations now we have? So you have two unknowns, eta. You have a Laplace equation that is satisfied. Okay. And you have this one. This is what you have. So this is how you solve the Laplace equation, where whatever in your domain. Now you may have other boundary conditions. If this only you have given only boundary condition here, and you don't know exactly what is happening, and at the end within the domain as x goes to, if your domain is only this one, and of course you have to give some boundary conditions for Laplace equation to solve it. Okay, that's how you solve. Because why you need two conditions here? Because you have two unknowns, eta and phi, right? In general, for Laplace equation, when you studied the partial differential equations, Laplace equation, one of the equation, you give the boundary condition. That is basically steady state heat equation. So there is no time involved, only spatial domain. Whatever Laplace equation satisfied, no, you have a boundary. On the boundary, you have to give the boundary conditions. What are the boundary conditions you can prescribe? The unknown phi may be, you may ask, you may give what is that quantity on the boundary, you may know. Or the flux, dou phi by dou x may be, dou phi by dou n maybe you may give, or the combination of that is called Robin condition, dou phi by dou n plus some constant times phi, that is zero you may give, or some other thing you can give. So those are the three possibilities you generally may see the applications. That is what Dirichlet boundary condition. If you prescribe phi on the boundary, that is Dirichlet boundary condition. If you prescribe dou phi by dou n normal derivative, that is your Neumann condition. So the other on the boundary, on the remaining boundary. So this is a free surface boundary. Okay. So these are the two conditions on free surface. Okay. So both kinematic boundary condition and dynamic boundary condition are on the free surface. On the free surface boundary. Okay. On other boundaries, for example, solid boundaries, you don't know, right? So water, if you want to contain, you may have some other boundary, maybe solid boundaries or whatever. So I'll just put it on other solid boundaries. Let's put it on the solid boundaries. Solid or whatever. So solid boundaries, what you do is, see, what are the boundary conditions? Boundary conditions can be, maybe, boundary conditions for the Laplace equation, maybe 1. Phi equal to phi is given on boundary. That is called Dirichlet boundary condition. Any question up to here? Get it clear, okay? So that you think, and so that everything is clear for you. So if you provide normal derivative on the boundary, means you have a normal, right? Outward normal. So dou phi by dou n is given. That is what is on the boundary. Of course, on the boundary, so you say this Neumann boundary condition. Okay. So other condition that we see is this is basically, this tells you that this, of course, given means it may be zero, or some heat, something is going out. Okay. some flux is going out. You may say that if dou phi by dou n is something else, that means basically the flux, the velocity, the volume flux that may be going out. Okay, that's what it means. Grad phi is nothing but your so that's why u is going out, u dot n. That is exactly the volume flux. Something is going out. That's what is the meaning. If it is positive or negative, something is coming inside. If it is zero, so basically it's insulated. Basically, the nothing is going out. Flux is zero. That is what is the meaning of Neumann. Dirichlet means you don't know. P is constant. P is some function is given. So you don't know exactly what it means. Okay. In the applications you may see P equal to constant means if it is a vibrating state. So if it is P means some steady state heat context. You say that it is like you're maintaining some temperature because phi is nothing but your temperature in the steady state case of the Laplace heat equation. Steady state heat equation is nothing but your Laplace. Have you studied partial differential equations? You have done, right?
Yes, sir, in third semester, sir.
So, are you understanding what I'm saying? All this?
Yes, sir, yes, sir.
Okay. So, yeah. So, ask me if you have any questions. So, the third boundary condition is it can be combination of these two. So, that is dou phi by dou n plus. So, let me write dou phi by dou n plus some alpha into phi is given. For alpha is strictly positive. Okay. This is called Robin boundary condition. Robin boundary condition. This is how you give and try to solve this. You may think of this fluid problem as water problem or whatever. Okay, because of G, you are looking for some solutions that you may see it as waves. That is different. Okay, once you involve, so such a phi is called velocity potential. So it acts like if it solves this, you may see some certain waves also, progressive waves, some disturbances. Okay, because of only G, you may see whatever flow is due to the waves due to only G. Okay, not allowing any other external force. That is what is the water waves you see in the ocean. Of course, you may see in the ocean, real ocean, you may see a lot of other forces like wind. Wind is also creating some waves. Purely gravitational waves. There is nothing else. Of course, many people are disturbing. No, those ships are going. That is also you are pumping in some energy, right? You are disturbing the surface. That may be creating a lot of flows. And of course, inside so many other things are naturally happening inside your ocean. So that is different issues. Here we are considering some simplest case. This is how you look at these equations. Okay, you understand these equations. This is how you solve. So if you simplify like irrotational flow, you want to put it, then this is how the problem is simplified. You are basically solving the Laplace equation. Okay, so this is one thing. Now, do you understand now? Hello? So if I remove this incompressibility,
Yes, sir.
you are not gaining anything except one equation you are integrating out. But that only you are not solving. Other equations as though you are solving and trying to you get your u and come here and put it here so that you are getting basically you is given in terms of, so pressure may be a nonlinear function, right? So if you actually see phi, actually it's a linear equation you are solving. So once you solve phi is a linear function. So what is the advantage of linear equations you are solving? That it is a linear superposition of solutions is possible, isn't it? So linear equation means any two solutions you can superpose is also a solution, right? So that's how you may solve for many p's and you come back and see that p, the pressure need not be linear, right? Because p is given in terms of grad phi square, dou phi by dou t. So if you have alone dou phi by dou t, it's okay, it's linear. If you remove this, linearize this one, this Bernoulli equation, then it may be linear. P may be linear, whatever you solve phi. Okay. So you solve phi1 and phi2, two solutions, and you come here and put it. P is also linear, but you have a grad p square. So that makes it p, that pressure p, which is actually you cannot simply add. So p1 plus p2, you cannot say that p1 plus p2 is actually simply a grad of phi1 plus p2, right? Isn't it? So you can't put, so p equal to, I can solve p in terms of this one, right? So P1 is corresponds to Phi1. So P2 is corresponds to Phi2. P1 plus P2 is corresponds to Phi1 plus Phi2. You can't say, right? Because it is not linear. So that is the advantage with this Bernoulli equation. Bernoulli equation, you can actually get your P in terms of this phi. Okay. So Bernoulli equation has many other applications for steady flows. For steady flows, what we have done? Now come back. That's what is finished. That is for irrotational flow. For steady flows, we already derived, right? For steady flow, that means dou u by dou t I removed. Of course, this is the steady flow. Steady flow means I am not considering rotational. Steady flow means what is that I am saying? I am not considering incompressible flow. Okay. Of course, irrotationality also I have not used. So this is purely I removed for steady general fluid. Okay. Neither irrotational nor incompressible, right? So what is that equation that you used? Your B, right? B is constant along the streamlines. That's what you have seen now. Streamlines, isn't it? Along the vertex lines also. That is what you have seen. What is your B? You basically have u bar square by 2 plus. Now I consider integral dp by rho. I consider simplest case like rho is constant. So that you can write like p by rho, where rho is constant. Okay. So if you consider the density is constant, then you can write it like integral dp by rho as simply dp by rho. Of course, plus p gg, gz equal to constant. Okay. This is what you have. Now, you see, this particular thing, if you consider only this part, that is exactly constant. If you consider, that is basically your what is that called? Statics. Okay, fluid static flow. Okay, what exactly you call? I'll just give you name. We don't use. What do you call such flows? Where you don't consider function of t, you removed it. What do you call? Let me just show you this one. Yeah, that's called. See, this is only, of course, hydrostatic. Of course, I think you are using only for incompressible. Okay, so basically you only used incompressible, right? So, but still, did you use incompressibility there in the derivation of steady flows? Yes. Did we use del dot u equal to 0? I think we used, no? Did we use? We have not, right? The derivation of that, did we use del dot u equal to u cross w, we put it, so grad p. So we have not used del dot u equal to 0, right? Yeah, that's neither irrotational nor rotational nor incompressible, obviously. Yes. Okay, so that's okay. So for incompressible, this is what, so this is basically hydro. So you say that static. So fluid statics. Fluid static equation is p by rho plus gg is constant. Okay, so that is also called hydrostatics. Okay, generally you apply for water, no? So water kind of fluids, incompressible fluids, if you consider, that's what you do. Okay. So basically what you are considering, there is no flow. So fluid static means meaning what? Since static means u is basically 0. U is 0. Okay. So U is 0 means what? If you how you get this equation? Just go back to your momentum equation. Momentum equation becomes, once you put U equal to 0, everything gets cancelled. So you're left with only grad, right? Dou U by dou T will go, right? Your momentum equation is what? Capital du by dt, right? So what is the momentum equation? Capital du by dt. This is your this one plus grad p by rho, okay, equal to, of course, your this thing is there now. So this is your force, external force, that is gg minus gg. Okay, that's the right hand side. You bring it this side. So this is what you get, isn't it? Of course, grad of that only we're going to write it, right? So this is it becoming basically gradient of gg this side. Once you write this side, this is how you got it. This is equal to 0, right? So what is the momentum equation now? Rho is constant. Is it possible for a compressible fluid? Rho is constant density. Density will change now. You compress it, right? So this you are removing it, correct? Since rho is constant, you imposed. So basically, compressible fluid which may have rotations. Rotation is not possible. No, there is no flow. Flow is also not there. So basically, it's rotational. Okay. So you simply have hydrostatistics. This is called fluid statics and hydrostatics. Hydrostatics. So in generally, you write hydrostatics. So you have class, no? Hello? Stop
Yes,
me.
sir. Yes, sir.
You want to go, stop me. So I'll leave it here. Okay. So what I'm trying to say is you have this part, this hydrostatic part, and you remove this part, and you generally, so you have something called hydrostatic, and then of course dynamic part. Dynamic part is there is a flow involving. So we'll touch upon these things, and in the process you may do some Archimedean principle, application of Bernoulli things. These things you may see again this side, that side. Okay. And whatever you have seen last class, at the end, you used two examples where through stream function we define stream function in two-dimensional flows. Similarly, once you have irrotational flow, there is a phi function, that is a velocity potential, through which also you can get your flows. Okay, whatever you can realize certain flows like simplest flows. Okay, that's what we are seeing. So we are at the juncture where we are going different directions, but you have to connect all of them together. Okay, so that's what is important at this moment. So I'll see you maybe on Friday. I will let you know exactly how I give you at what time I will give you this one. Okay, plan. Because 12th I'm back only at 10:30, 11, so I may miss your class. So evening I will I'll come and I'll send you the link. Watch out for the link on Friday around afternoon sometime. So most probably in the evening I will take. Okay, so that this week I'll finish like that. Okay, next week maybe usual way we can do. Fine.
Okay, sir.
Yeah. See you. See you. See you tomorrow. Yeah. Bye. See you on Friday. Thank you.